to run everything through the browser now, which is not the perfect solution, but we'll have to stick with that. My X server didn't want as I wanted. Okay, what I'm going to talk about today is sctp, which is a new transport protocol that has been defined by the IETF. Just out of curiosity, who has heard of sctp before? Anyone here? Okay, thanks. So I'm just going to see what I'm going to talk about right here. So I'm going to have a look, just short overview of sctp, the development, some of the terms that are usually used in sctp, contrary to TCP, for example. I'm going to have a look a little bit at the wire format, so what you're going to see on the wire if you do sctp. Then I'm going to go into the protocol details. I'm going to have a look at how connections are set up and terminated. And then I'm going to have a look at one of the important features of sctp that make it superior to TCP, for example. One is the stream concept, and the other one is multi-homing support. Then I'm going to give a short wrap-up, probably. I'm sorry. Okay. And then I'm going to give a short wrap-up and have a look at what's out there, what you can get from sctp. Okay. First off, well, in a nutshell, so to speak, sctp is a new reliable transport protocol that sits at the same layer as TCP and UDP do. It's reliable and it can be used together with TCP and UDP in an operating system. Some of you may have seen that some of the newer releases of Linux have incorporated sctp, although that's not really stable yet. sctp is message-oriented. That is, the message delineation is incorporated into the protocol, contrary to what TCP gives you. TCP just gives you a stream of bytes that starts at some point, which is split up by TCP into packets that all have the maximum segment size. sctp is message-oriented, supports multi-homing. That is, you can have endpoints that have more than one IP address. And this is a really new and interesting feature. The other feature is you have so-called streams. And what sctp calls streams are streams of messages. You may have several of these streams per connection, and you may multiplex several logical connections into one association, into one sctp association. Also, some lessons learned by TCP, what TCP has done wrong in the past. The people that designed sctp try to improve. That's features against denial of service and blind attacks. First off, this protocol was developed in the SIGTRAN working group of the IETF. That's a working group that deals with transmission of signaling data over IP-based networks. And signaling data here means data for setting up calls in the broadband carrier networks. So this is not what you see when you get ISDN, not really what you see when you get ISDN. Well, the people, of course, looked first at the protocols that were there in the IP, in IP-based networks, and there you have UDP and TCP. Initially, the standardization started with a protocol that's set on top of UDP, because they wanted message-based transfer. And at some point, they decided, well, very late in the cycle, they decided that they move the whole thing one layer down and put it right on top of IP. At that point, all the people that were in the standardization, that were working in the transport area working group, where TCP standardization is done, they really first learned about this protocol. So this was sort of a standardization tactic, also to get this around the people who prefer TCP for some reason. All this happened, or happens still, in anticipation of the future networks will have not only voice and signaling data, but also IP-based data for mail or whatever you have. There are some solutions for third generation partnership project networks. That's the UMTS network that are purely IP-based, which is IPv6. And right now there are already some RFCs out there that specify adaptation layers that use sctp as underlying transport protocol. And these adaptation layers require for a safe and secure and efficient signaling that the transport protocol have features such as sctp does have. Okay. These are some of the other adaptation layers that have been specified. They are already RFCs, and these exist for transporting the data that is used for establishing core control, for establishing call setups in signaling networks of telephone carriers. And these will in the future be carried over IP networks, and that's really the interesting, or one of the interesting points here. Right now there are there's still a lot of activity around sctp. As with all new standards, you have some bugs, you have some features that are not as they should be. And these features have been improved or are being improved, and there are drafts out there who change, for example, or who add some features to sctp that are there for a partially reliable data delivery, which may be useful for multimedia streaming. And there are some other things out there. The implementer's guide right now is the document that corrects the usual bugs. Okay, here's one of the application scenarios. Now this comes from the convergence of carrier networks and IP networks, really. The idea behind this is that you want to have cheap clusters of PCs in the IP network that deliver the services. For example, the ISDN user part, which is the application or the controller of the ISDN signaling backbone. And these user parts can be used unchanged on IP-based boxes, and the underlying protocols, which is the MTP3 user adaptation layer and sctp IP combination, they offer the same interface to the ESUB as does a usual PSTN switch in the backbone networks. And now you have machines on the networks that are the signaling gateways, and the signaling gateways sit at the boundary between these two networks. Okay, there's another number of other application scenarios which I really do not want to go into right now. I'm going to just have a look, give you a few details about the terminology which I will use here. First off, a transport address, and this is probably nothing new to you. Here is a combination of an IP address, and that is IPv version 4 or version 6, and an SCTP port, because SCTP uses the same port concept as UDP and TCP. Then what frequently is mentioned is a protocol endpoint. Protocol endpoint is the logical sender and receiver, and is defined by a unique set of transport addresses. Now, this is not a host, it's just an instance of the SCTP protocol, running on a host, of course. The term association is the SCTP parlay for a connection. So what you would call a TCP connection here is an SCTP association. This has been given a different name because here we have a concept where you can have a lot of IP addresses because SCTP supports multi-homing. Okay, the path. As a path is defined a route that is taken from one host to the other host, or to one specific destination address of the other host. So if you're a host with 2 IP addresses and I am a host with 1 IP address, then I have 2 paths to you. Okay. And you can have a number of these, as I just mentioned already. And within a stream, usually messages are delivered in order. So this means you have several reordering queues, and I will show that later again, a little more in detail. Finally, a chunk is a unit of information in an STTP packet where you can bundle a number of data or control chunks within one STTP packet and send this via IP. All right, now we go a little bit more into the details. This is the wire format. First of all, the IP protocol number for STTP is 132, which has been standardized and defined by the IANA. Every STTP packet, and this upper part comes directly after the IP header. Each STTP packet has a common header. The common header contains 3 or 4 things. The ports, source and destination port, exactly similar to TCP and UDP. A verification tag, which is a 32-bit integer, and a 32-bit checksum. So the checksum here has been the subject of much debate in the ITF. First off, well, this may also be a standardization issue where you want to delay things, where you want to delay deployment of things so that you get some advantage over your competitors. Anyway, the checksum has been changed about half a year after the original RFC has been published. It's now a 32-bit cyclic redundancy check, which is supposedly stronger for short messages than the checksum that had originally been specified there. You have a verification tag, which is 32 bits, which makes this thing harder to attack. You cannot insert a valid STTP packet into an existing connection if you don't know that tag. And you do not know the tag if you are a blind attacker. So this is one of the features that has been added here. And then you see that there may be 1 or possibly more so-called chunks. And these chunks may contain data, obviously, but they also may contain information for control purposes. All right, here's all of the existing chunk types. Well, not all, but the most important ones anyway. You have 4 chunks for the setup of the association, and we're going to have a look at how the association setup works a few slides from now. You've got the association teardown. There's also, well, actually 3 chunks. You've got the abort chunk, which is sort of like a reset in TCP. It's a hard abort of a connection. You've got the shutdown act. Well, shutdown complete is missing there, I'm sorry. So there's 3 chunks for the teardown. You've got the operation error, which can be sent with an abort to tell the peer why you terminated the connection. Okay, the real important chunks for data transmission are the payload data chunk, and the selective acknowledgement chunk. So selective acknowledgement is also an SCTP, not only in TCP as an enhancement, but it has been incorporated into this protocol from the very beginning. And finally, you've got for the management of the paths, for finding out if a path is still up or not, you've got 2 messages, a request and an acknowledgement. So it's like a very simple ping thing that can be sent to the peer for finding out whether the path is still there. Some of these chunks have parameters, and this is also a very simple thing. For example, if you set up a connection and you have a large number of IP addresses, then you need a way to add these IP addresses and send them to your peer. And this is done in parameters. So actually the IP address parameters are the mostly used parameters, although the init-ack also has a so-called cookie parameter. And what this is, I'll tell you later. The format of these parameters here is very simple, similar to the chunks. You've got a type and a length field, and then the actual data. There are provisions for peers that do not recognize some parameters. Well, you can report an error. How the answer must be, but this would go into too much detail here. So there are a number of solutions for the special cases of protocols. Okay, as one example of a chunk, which is probably also the most important chunk, I've put down here the data chunk. The data chunk carries two distinct sequence numbers. You've got a 32-bit transmission sequence number, TSN, the usual type and length field. You've got three flags. The first flag is the unordered flag. When an endpoint gets a message with the unordered flag set, then he can directly give it to the user of the protocol. If the unordered bit is not set, the message must be delivered to the user of this protocol in sequence. So you've got to wait for other maybe lost messages that come before this message. Then you've got the stream ID, which is a 16-bit value, which means you've got 65,535 streams you can use. And you've got a stream sequence number, which also is 16-bit. And the stream sequence number is now used to reorder messages that belong to one certain stream. Then you've got a payload protocol identifier. This is needed because data may be passed for different applications on different streams within one association. Now this one association only has one port, which is the usual standardized port. And when middle boxes that pass on SCTP or do not pass on SCTP, they need to know what's in the data. And they need to look into the chunks, and they need to find out the protocol ID of the data, and then they can find out the type of application. So this protocol ID is standardized for example, for the MTP adaptation layers I showed you before. Well, the overall overhead are 16 bytes per message, and this is more than TCP. No, TCP is 20. Well, you've got another 12 bytes for the SCTP header. So the overall overhead for sending one SCTP message that has the maximum segment size to TCP that sends a maximum segment size is like 8 bytes something. No, more. Okay, it's 16 and 12 is 28, so 8 bytes, yes, is the overall overhead you have against TCP. So SCTP does perform a little worse with this respect. The other flags, begin and end, B and E, may be set if you fragment a large message, that is a message that is larger than your maximum segment size, into several data chunks. They can be reassembled later on. They will have all the same sequence number, the stream sequence number, but they will have different TSNs then. Okay, now here's how an SCTP association is established. That is really very simple. Host A tries to establish an SCTP association with host B and sends the init chunk alone by itself. And this init chunk may, as I just explained before, contain a list of IP addresses. Let's say you've got A1 and A2, so 2 IP addresses. Host B now will return an init ACK to confirm that he got the init. He will add the list of its own addresses, B1 and B2, and he will list a cookie. He will add a cookie. Now, the cookie is a parameter that is chosen by host B, so only host B knows what's in the cookie, and that is signed by host B. So if A changes anything in the cookie, when this cookie is returned later, B will probably not accept the cookie if the signature is okay. Um, Now the cookie contains all the data B got from A with the init. So actually this cookie contains probably all the data that plus in clear text the addresses of B1, B2. And then B would forget anything about this init. So B will not allocate any resources. Well, then very simply, host A returns a cookie echo, which is a very simple chunk that only contains the cookie that he received from B as a parameter. And B is going to verify the cookie. Now, if the cookie signature is okay, then he will accept the cookie, he will allocate resources, will enter the state established, which means that there is an association for both of the hosts, and will return a cookie echo. The last two packets, I must say, may contain as add-on chunks after these control chunks, data chunks. So the last two legs of the association setup may carry data. Okay, very simple termination of the association. Well, the one thing I just mentioned before really quickly is the abort. This abort is done due to some fatal condition in host A, for example, or due to the fact that he received an invalid incoming init message or something like this. Host A will just send the abort, will return the current verification tag in the abort, and host B will know that A has gone if the abort arrives. If not, host B will find out anyway later on. But this is just to simplify things. So this is the hard termination. There's also, of course, the mean for graceful termination of an association. At some point in time, the application and host A says, I'm going to close. I'm done. Then host A is going to flush, or the protocol, and host A is going to flush the queues. It's going to send a shutdown if all data has been acknowledged by host B. And host B will receive this shutdown, will learn that host A wants to terminate the connection, will also see to it that he gets rid of all the messages he still wants to send, and will send the shutdown act. Then to terminate the connection finally, host A returns the shutdown complete, and then both sides are set and the association is done. Of course, here you've got the usual timers, you've got the usual retransmission limits and stuff like that to make sure that if some of these messages get lost, at some point in time, both of the hosts will recover and learn that they're gone. Okay, as I already mentioned also, one of the important concepts that, well, sctp will probably do better than TCP is the fact that it can overcome the head of line blocking that TCP inherently has. Head of line blocking appears or comes into play when you have a lot of messages that do not really depend on each other. This means one of these messages could be lost in the transmission. And well, then you've got like two messages. Well, let's say we've got messages 1, 2, and 3. One gets lost on the way, and 2 and 3 do not really depend on message 1. Well, then message 2 and 3 will wait, or will have to wait in TCP until the retransmission is come, and message 1 has arrived, and only then will TCP, because this is the semantic of TCP, only then will TCP deliver the data to the upper layer. This means you could actually deliver the data, messages 2 and 3, to the upper layer because you do not really need to wait on message 1. And this exactly is what sctp was made for, and why you have two distinct levels of transmission sequence numbers and of sequence numbers at all that can do exactly this. Now, reordering within one stream, and you saw in the data packet that there were stream IDs, so you know that a certain message was destined for one certain stream. And within this stream, you've got a reordering queue that will deliver the data according to the currently needed or currently arriving stream sequence number. Just as a side point, the beginning when the association is established. And streams are unidirectional. So it may very well be possible that I have like one stream to my peer, and the peer has 10 streams coming towards me. Just little graphics, and then you'll probably see at once what's meant with the head of line blocking. Suppose we've got 4 distinct processes that are all waiting for data. And we've got 4 streams corresponding to these processes. Now, on the left side, you've got the blue queue, and this blue queue can deliver the first message because number 1 is the first sequence number. It delivers this message to process 1. This one is really waiting on the application, so we've got messages 1 and 2 waiting in the queue until the application gets it. Here in the red queue, we've got messages 17, 18, and 19. And these are waiting for one message that comes before these. That is message 16. And on the right side, the light green queue, you've got the message 4 that's just being delivered to the application. Now, if this new packet arrives here, which contains the blue sequence number, stream sequence number 2, the orange stream sequence number 3, the stream sequence number 16 for the red queue, and the 7 for the green queue. This new sctp packet, these messages will be assembled or will be delivered to the stream queues. And in the next picture you see what's happening if these reordering processes have been done. Well, here we saw that message 1 was delivered to process 1, and message 2 can be delivered because it's the next one. Here, the process 2 got the first message out of the queue, and message 3 gets at the tail of the queue and waits for process P2 until it gets the message. Then on the red queue, you've got the messages 17, 18, 19 going up one place in the queue because in the last packet, message 16 had arrived and can be delivered right away to process P3. And now 17, 18, and 19 can be got by process P3 too. And in the right one, we had in the last picture the message 5 delivered to process P4. And now the next message that arrived was message 7. So we may think that 6 maybe got lost on the transmission. And this right queue is blocked, but all the other queues can deliver data. So this is really what's the good thing here about the stream concept. Okay, the other important point is multi-homing. Well, suppose, and this is pretty much the same scenario that I mentioned a few minutes ago, you've got one host that has 2 addresses, A1, A2, and you've got another host that has an association with this host A, which is host B, and B has the addresses B1, B2, and B3. So this is sort of an asymmetric scenario, and it's rather interesting what can happen here. Now, first off, the standard defines that one of the paths that you have towards the peer is chosen as primary path, and you are pretty free in choosing this path. So you can choose either of the 3. Let's say we've got 2 paths, one going from A1 to B1, and the other one going from B3 to A2. So this is done basically by the transfer protocol and the routing table of the hosts. The primary path carries the main data load. All other paths, according to a standard at least, carry nothing but retransmissions if messages are lost on the primary path. And the other paths also carry heartbeats. The standard says around all 30 seconds you should send one heartbeat message to each path, to each destination path address. Now, this means if host B gets a heartbeat arriving on address B2, he will send a heartbeat ACK to the source address on host A. Okay, one more thing. Each path has a state, and the state can be either active or passive. So you really trace the. You have a look at the state of the path, and you have got error counters, error thresholds, and if you send a number of heartbeats towards the path and you do not get a return within a certain time, then the path will have failed. Okay. Also worth noting is the fact that for each destination path address, you keep a separate set of congestion parameters, round trip time, estimates, and these things. And well, as I mentioned, congestion control. For each path, you have to have a TCP-friendly flow control, which is pretty much, as you know it from TCP. We had done measurements like 2 years ago. I had compared an STP implementation and TCP implementation, how these two split up with a limited bandwidth, and found out that both were sharing the bandwidth pretty much equally well. And this is, of course, vital for internet deployment, because if not, you've got a problem. Now, let's assume that one path fails. For example, someone pulls a plug to the internet, a plug to the switch or whatever. You will have retransmissions on the primary path because the primary path has failed. These retransmissions will take a secondary path. So we've got either path to B2 or B3 in this case. And with each retransmission, A will increase an error counter, and at some point there will be a threshold that's exceeded, and A will know that the path has failed to B1, and A will say that the path to B1 has failed. And this one is going inactive. At that point, an application gets a signal and may learn or may set another primary path, for example, a path to B2. This means the inactive path is not used anymore. If a new primary path has been set, there will only be heartbeats. And if the path comes back at some point in time and the heartbeat goes through, then the path will be reinstated and will get active state again. Okay. Now, one of the things that's really interesting here is the trouble you get if you do such a solution, because you all have a routing table. And now what happens if your secondary path, the new primary path you choose, is a path that has as a default exit route A1, which is the link that has failed. At this point, multi-homing may not help you at all. There are some solutions out there which have been incorporated also in, I think, the BSD implementations, where you have several default routes, and you just change your default routes if the HTTP protocol recognizes that something like this has happened. But this is not very simple. Okay, I just mentioned some of these before. Well, from the lessons you learned from TCP, we've got this feature against denial of service and SYN flooding, which is we use a cookie and only allocate resources if the cookie signature is fine. We use a verification tag, which is negotiated in the association setup in the beginning. And this is a 32-bit tag, and it's very hard to just guess by this random number, unless you use a weak random algorithm. Okay, now I also want to mention especially that SCTP does not contain any strong security features. So if you're a man in the middle there, well, you get anything. It can also attack the endpoints, of course. So there is no change to TCP with that. Well, if you really want strong security, you need to resort to either IPsec or you need to use TLS on top of sctp, which also has been standardized like 2 weeks ago. Well, which I've written with. A little bit more back again to the practical things. There are a number of implementations of sctp out there already, although most of these tend to be a little more experimental or tend to be a little better still. First off, we developed a userland implementation, which is the first one together with Siemens in Munich. There is an implementation available under GPL from Randy Stewart, one of the co-authors of the sctp RFC, who also has written the BSD KMI snapshot, the sctp implementation that comes with a KMI snapshot for BSD systems. More interesting, though, is the fact that more or less all operating system vendors, I mean, if you look at the operating system, you could say all operating system vendors, have started implementing sctp into the kernels. There is a draft right now that specifies how programming is done with sctp. So there will be a socket interface, which is not very simple, but since you have a lot of problems with multi-homing, you need to have new functions that have not been before, there before with UDP or TCP. You need to have, for example, an option to add addresses or delete addresses. Cisco delivers sctp, I think, already in iOS. They have also a product which is the IP transfer point. This is a product that can be used for offloading signaling, SMS signaling mainly, which is not so time critical, to IP networks. As I said, BSD has sctp in the KMI snapshot in the kernel. There is a project, Linux kernel sctp, LK-sctp. They have started merging this into the mainstream developers kernel, somewhere around 2520. Solaris, IEX, HPUX, and Compaq. I don't know about these, but AIX has a team from IBM. Another team from IBM works on the Linux kernel too. And products are made also by telco companies. So we've got Motorola, Cisco, Ericsson, Nokia, and some other smaller telco companies that develop sctp protocols. There are regularly so-called bake-offs, which are, well, hacking events more or less, or interoperability tests of sctp implementations. One of these events was at the University of Essen here in September, and that was really a fun event. But still, the implementations you have are, well, a little buggy. So it might be interesting to, if you really have time to code, go grab a Linux kernel, get on the LK-sctp mailing list, and help these guys. They need it. All right, I'll be pretty much at the end soon. I'm just going to have a look at the applications that are currently being standardized. Now, I've already mentioned the MTP adaptation layer, for signaling system number 7. HTTP over STTP is interesting, sort of works as a hack, but it might be worthwhile to investigate how you can really use the multi-streaming feature of STTP together with HTTP. Because if you have different media, it might be very interesting to just deliver text on one stream and multimedia data on another stream, maybe. There is a draft, an ITF draft for SIP over STTP. Reliable server pooling will be a user of STTP. STTP is recommended for transport protocol for the AAA diameter, which will be the successor to radios, SCSI over IP, and the IETF RDDP working groups. They all discuss STTP really as the only transport protocol. Okay, To extensions, I will not go into too much detail with these. There is a draft for having partially reliable data delivery, so you can give data chunks a lifetime, and if the lifetime is exceeded, they will not be retransmitted or will not be transmitted at all. This is very interesting for multimedia streaming. Another thing is dynamic address reconfiguration within your associations. And this way you can really add addresses to existing associations, or you can take them away from existing associations. And this is a nice thing for mobility. Okay, now really the wrap up. sctp will soon appear on your radars. If you have looked at Ethereal, for example, you've ever wondered what this sctp was, it's there already. Key features of sctp are message framing, multi-homing support, multiple stream support, so independence of data delivery. sctp is an important protocol for all telco companies that want to develop products for convergence of traditional PSTN networks and IP networks. And it's not really an easy protocol. So there are a lot of special cases, and the RFC is rather long. And it's a neat playground for hackers. So with that, I'm pretty much through, and I can take some questions if you have some. I have some links, which you will find also on the web then. Okay, anyone? Right here.
With HTTP, the host has to know all its addresses, and the common sense is to have not the host know the addresses, but some router. Is there any way to not make every host a router and handle all that stuff?
No, it's really very simple. I mean, if you have a PC, you've got 10 network cards added to the PC, and you can give each network card an address. Or imagine just
I don't want it. I'm in a small network, and then that network connected to several internet backbones, whatever. You don't want to configure every single machine on the local network, but only maybe the router handle all that stuff.
Okay, I suppose use IPv6.
Yes, I have two questions. The first question, are there any implementations to have network address translation or masquerading for SCTP? And the second question is, how many routers in the internet and how many brain-dead firewalls are blocking this right now when I want to play with it?
Well, I'm just going to have a look here at the multi-homing image real quick, where network address translation is really a problem. It's a pain in the ass, as you might say. It's really impossible to track the state of one associations if your firewall is, for example, sitting at address B3 and the init packet goes to B1. And you've got a problem. So NAT right now there's no real solution for. And as to the routers in the internet, I'd say that probably a lot will block them. But we had some very nice, sort of terminal connections, sort of like, what's it called? Some talk exchange between here at the University of Essen and some guys in Chicago. So it will go through the backbone. It will probably be blocked by your well, if you have like a company network or something like that, there it will be blocked because we need to talk to our university administrators to get free access for that. Okay.
Okay, about multi-homing. What do I need another implementation of multi-homing for at the transport layer when I already have multi-homing at the network layer?
Well, the problem is that currently transport protocols do not support it. So how are you going to use your multi-homing with TCP?
BGP should handle that for me?
Well, the fact is, you can use all of these at the same time. You do not need to reconfigure any routing. So BGP is a whole different problem there. So you can send data on all of these paths at the same time. So this is a transport protocol, and this will allow you to send at the same time or just one after the other to all of these addresses with one established connection.
But the main data. But the main data is only sent through the main connection?
Yes.
So
Well,
there's no real load balancing or anything like that?
No. That's one of the research issues currently.
So that might get into the protocol someday?
Well, it really depends on your application and on the interfaces that you get from your application. The original RFC did not have the socket draft. So there was no socket interface defined, which will be implemented by all operating systems. The original RFC had an API that allowed for sending the address you'd send your data to. So you could say, I send the first message to B1, the second message to B2, and the third message to B3.
If different applications want to speak to one HTTP service at different times, can they reuse or can the streams be bundled into one association? So if there's already an association between two hosts and another application one, can it enter this association, or is another one set up for these streams?
This is really done on a per process basis. So if you've got a new process, this is the same thing as TCP. You've got ports, and you will choose a different source port.
Are there any efforts to incorporate multicast or broadcast scenarios?
Well, multicast addresses are prohibited by the RFC, so no. Unfortunately not.
One picture in this picture is a path A1 or A2, or is it a combination of one of the A's and one of the B's?
For one host, a path is one destination transport address to its peer. So host A has 3 paths to host B, and B has 2 paths to host A. Because just as a side note, your routing table in your host will tell you where to send, or will tell you how to select the source address of your packet. Unless there are SCTP implementations who enforce selection of the source address, which might be possible too.
Okay, about congestion control, are they similar? Is it the same as TCP uses? Are there differences? And TCP has some problems with the congestion control. Did they use the chance to fix those? For example, fairness, for example, instability in high bandwidth delay networks. And the third question is, ECN, is it also defined for SCTP?
Yes, well, let's start with the back. ECN is or was added to the RFC and will probably be supported by most of the implementations. Because at the time the RFC was finished, it was not yet officially released, ECN. Then what's the question before? Okay, the congestion control. Congestion control is similar to the last standardized TCP congestion controls. So there was some, I don't know the RFC number, but there was some of the latest flow control standards that were used for TCP.
Okay, but it's still the same AIMD algorithm.
Exactly. Yeah.
And
It's additive increase and multiplicative decrease.
Yeah. And the timers, what is the resolution of the timers?
Timers really depend also on the operating system, but you do have some values given in the RFC, which are very path. And I know the minimum timeout is 1 second for a path, and you start off at 3 seconds. So you do have rather large times for a standard sctp, which is not really nice for failovers. But we have also researched failovers with our implementation in the lab, and we found that in certain conditions you can have a failover time of less than 500 milliseconds and still have a protocol that reasonably works. Okay, well, I'd like to thank you very much.